So, while we're getting started, if we could get a sound check, that would be great. Anything we can check? So far, yeah. So before we start today, announcements. There should have been posted the class invitation for the face-to-face lecture, I believe last week, that will carry us through November 20th. There is an exam this Friday, covers up through and including material that we finished last week. So that's everything from fluid properties to forces on submerged surfaces. If the exam rooms and who is going to be in each room was posted today, just before class. If anybody has an issue with the exam specifics, meaning date, time, room, they should have contacted me last Friday or earlier. But if not, you need to contact me after class if, for example, you can't make it. We need to try to arrange something. Are there any questions from when we last met? Yes.
The exam's still at 2, right?
The exam is at 2 to 4 p.m. and it's face-to-face in one of the 2 working rooms, I believe. They actually gave us 3 rooms. And it's open book and 1 crib sheet. And on that crib sheet, you can write anything you want on any of the 6 sides of the paper at whatever font you want to put. All right. The idea is instead of open notes where people, as the closer and closer you get to the back of the exam, the end of the exam, people are flipping through notes and just making a lot of noise. That 1 sheet, you know, you can be turning back and forth. You're not a distraction to everybody around you. And the open book, again, if you have an online version of the book, I think the TAs will tell you where to sit. If I recall, it's the back of the room, just so they can look over your screen and make sure you're not, you know, surfing the internet. And also, you shouldn't bring a phone, but if you really have to bring a phone, turn it off. You get a little anxious when phones are going off, as well as when people are looking at their phones during the exam. So just keep it out of sight. So were there any questions from online? Question?
Do we have to use like the FE calculator or is any calculator good?
Any calculator is fine. I still have my Hewlett Packard that I had as an undergrad, and that's when calculators first came out. And if you have addition, subtraction, division, multiplication, and the trigonometric functions, you'll be fine. That's basically all you'll need. Any chat questions? That you can answer those. So this is review. This is where we were, and this is to get us moving forward. So we theoretically developed courses on plane submerged surfaces. And basically what we identified was that for any submerged surface, to calculate the magnitude of the resultant force of the pressure distribution on one side of that surface All we really need to do is locate the center of area. That center of area gives us a pressure at that location, PG. PG is the pressure at the center of area. And then the force is just the total area of that plane surface times the pressure at the center of area.
One of the students asked you to share the screen.
I'm
Yes,
not
I
sharing my screen. All right, I knew I was going too good. Check the chat box to see if that's okay, please. And I will then continue. So, with that magnitude, since the force is a vector, we need to know where it acts. And for a plane surface, what we really need is an x, y coordinate. The y coordinate is, of course, an inclined axis. The y-axis is an inclined axis, and the y distance from the free surface to a center of area, to the center of pressure, is the location along that y-axis from the free surface to where the force will act. And what we found for that is, again, if we have some inclined surface, the y-axis increases from a free surface, and we made the derivation from a free surface. That's why it's important to know where it is. Earlier, I had done an example where we had an enclosed container which did not have a free surface, but we could then calculate where the free surface should be. Do you have to know where the free surface is to get the magnitude of the force? No. All you need to know is the pressure at the center of area. And you know the pressure varies linearly across the surface. But for the location of that force, that's where you need to know where the free surface is. So what we developed was, again, if G is the center of area, we were calling CP the center of pressure, and we're measuring that from the free surface, YCP. So that's equal to the moment of inertia about the centroid of the area, IG, divided by the distance from the free surface down to the center of area, y bar times A plus y bar. And we identified that as the depth of submergence, y, for this plane surface gets larger and larger, that first term tends to 0, and the center of pressure moves closer and closer to the center of area. And then similarly, the other coordinate for where the force acts is the lateral coordinate along the surface, into and out of the paper, into and out of the board. And we did that derivation, and we came up with something called the product of inertia, IXY. And what's convenient for most engineering types of designs, we typically use very symmetric surfaces, circles, semicircles, squares, rectangles, and therefore it's almost self-evident where the center of area is. And if you can draw the y-axis through an axis of symmetry, then IXY is 0. And so typically you will have, for example, for a rectangle, you know where the center of area is, and therefore the center of pressure acts directly below it. Because that line through the center of area and the center of pressure is an axis of symmetry. So again, if we're looking at this figure, and this is our rectangle, again, the center of area is G, and the y-axis, as we have drawn it, is an axis of symmetry. And so IXY is 0 without any axis of symmetry. The other way to look at the force is that the force is equal to what I termed for you the volume of the pressure of the prism. So when you take this term, pressure at the center of area times area, basically what you're doing is calculating the volume of the pressure distribution, or what we call the pressure prism over the surface. Is that an easier way to calculate than PGA? I don't think so, but again, it's another way of thinking about it, and you'll get the same answer. And again, the resultant force acts at YCP, XCP. If you're looking at it as the pressure prism, that resultant force acts through the centroid of the pressure prism, just like weight, when we look at it in the vertical direction. The weight for any object acts through the center of mass, right? So it's a similar type of a concept. And then the last thing we talked about was how we could take this resultant force F. So for example, this resultant force F, and we could break it into horizontal Fx and vertical components. And when we looked at it as far as components, on the next slide, the resultant force, if you're breaking it into components, is the vector sum of the horizontal and vertical force. The line of action would be found by a moment equilibrium. Is that easier than calculating YCP and XCP? I don't think so, but if you think it's easier, you can certainly do it that way. You should get the same answer. For those two components, the horizontal component, what you have to do is take that inclined surface and you project it into a vertical plane. It's like taking a flashlight and flashing it on the object and looking at the shadow on the vertical wall. And that's now what you use for the inclined surface, quote unquote. That inclination, since it's on a vertical wall, is 90 degrees. And that gives you the horizontal component of that force. So again, under this horizontal component of the force Fx, you project the surface into a vertical plane, compute the projected surface height. The width should be the same as the natural surface that's not projected. Compute and then employ the theoretically developed equations on the projected area. So what I mean by that, we had F is equal to PGA on the last slide, which is the generic form for any inclined surface. But now what you're doing is looking at the X component, and you're looking at the horizontal projection characteristics. What's the pressure at the center of area of the horizontal projection? What's the area of the horizontally projected surface onto a vertical plane? And again, that force acts with the center of pressure on the projection, which can be calculated the same way as before. This means XCP and YCP. So you can use those same equations, but you're using them for the projection. And then the vertical force, as we identified, you're talking either for an inclined surface, the fluid is either above the surface or the fluid is below the surface. And what you have to do is think of the pressure distribution. If the fluid is above the surface, the pressure distribution is always normal to the surface, but if you look at the Z component or the vertical component, that pressure is pushing down on the surface. So the resultant force vector would have a vertical component acting downward on the surface. However, if the fluid, again, is below the surface, then the pressure distribution down here on the lower portion of the surface is normal to the underside because the fluid's below the surface. And in this case, this pressure distribution has a vertical component that's pushing upwards. And so the vertical component is in the upwards vertical direction, or positive Z. So when we're looking at the vertical component, we are talking about the magnitude of the vertical component is either the weight of the water that's physically above the surface, but if the fluid's below it, it's the weight of the water displaced by that would have been above the surface. And that force acts at the center of the volume. So we did an example with that, and that's where we left our last class. So what I want to talk about today is basically we're going to use the same concept we just talked about, only now extend it to curved surfaces. So for example, you've seen tanker trucks with fluids moving down the highways, and the ends of those tanker trucks are curves, and very commonly the sides are curved surfaces. So in order to specify the welds or the bolts or whatever fasteners to hold that thing together, we need to know the forces that are occurring on that system. So here we have a curved surface. And if we look at the vertical direction, Z was downwards, H was positive downwards, or we'll just say this is the Z direction. We know that pressure increases linear as we go down through a fluid. So we have this curved surface now, and it's submerged somewhere in this fluid. And we're either looking at the the left side of the surface or the right side of the surface. We're always looking at these types of problems as the fluid being on one side of the surface. And on the other side, there could either be no fluid, so atmospheric pressure, or it could be a completely different fluid. But the mechanics are the same. We're only calculating a force on one side. So in the vertical, you can see, again, that we have these pressures, and these pressures are operating all over the surface. But again, we look at the pressure distribution as being normal to the surface. So if we look at the pressure distribution, what you have is this curved pressure distribution everywhere normal to the surface. And again, when we integrate that pressure distribution, we're going to get some resultant force. And instead of going through a theoretical development like we did before for a plane submerged surface, well, we could go through a theoretical development, but you would need to know the equation of that line. So if it was a parabola or a semicircle, you could build that into the integration. But conventionally, what we do is take the components So we will look at that curved surface and independently calculate the horizontal component, just as we did for a plane submerged surface, and a vertical component, exactly how we did for a plane submerged surface. The horizontal force will first take that curved surface and shine a light on it and project it into a vertical plane. So if we take, for example, let's call it a hemisphere, half of a circle just cut in half, and we shine a light on it, what we'll see on the wall is a circle, right? And so the geometry of a hemisphere, when you look at that curved surface, is a pretty challenging equation to throw into the integration as we did before for a plane circle. But when we look at just a simple circle on the wall, it's easy to calculate the force on that circle and where it's going to act. Likewise, for the vertical force component, again, the fluid is either above or below the surface, but the vertical force component is just going to be the weight of the fluid that is physically above the surface or displaced by the surface. So if we look at a semi-theoretical development, if we look at dA, dA is so small that it's basically a little plane surface. So here's our dA. It's incrementally small. And so that's why on each little incremental surface dA, we have an incremental dfx and dfv. And again, all we're saying is at the differential scale, we can certainly take this surface, break it up into components that are basically plane submerged objects, and use everything we talked about before. Ultimately, when we integrate over the entire surface, all we're doing is integrating or summing the horizontal forces on this curved surface or the vertical forces. And so as I stated before, the horizontal force is the force acting on projection into the vertical plane, and the vertical force is just the weight of the fluid above or displaced by the surface. So I'm going to do an example. I just wanted to kind of get into this. I think I've talked about all this. So here's, I'm going to give you a tank, and you'll see it on the next figure. And what we want to do is just calculate the force on the end of the tank, which is going to be a curved surface. The fluid is water, but also we want to identify the line of action and the location of this force. So this is what our tank looks like. And that red area is a portion of the tank where we want to calculate the force. What's the force on the end of this tank? The end of the tank is a quarter circle, and it has a radius of 6 feet, as you can see. You can also see in this problem that we have a submergence of this curved surface. So we see a free surface. Remember, the fluid in here is water. And since all these dimensions are in feet, we're going to work the problem in our system of units, feet, seconds, pounds. And again, when you're doing the exam or the homeworks, you take the cue from the way the problem is given to you. If the problem's given to you in metric, then do the problem in metric. If it's given to you in BGS, do the problem in BGS. So if we know that we have 3 feet of submergence to the very top of this, if we take this curved surface and project it onto a wall, it's going to appear as a vertical plane. Now, I haven't given you the width of this tank. Let's just say it's 1 foot wide. We're doing this problem per unit of width. So if it's 1 foot wide, when you project this surface, this curved surface, into a horizontal plane, what you get is a surface that's 6 feet high by 1 feet wide. It's a rectangle. That's the projection of the curved surface. And I think for the rectangle, we all know that the center of area is halfway down from the top. So if it's 6 feet high, it's 3 feet down from the top. And if it's 1 feet wide, it's a half a foot over from each side. And since we know where the center of area is, again, if it's 6 feet high, from the top of the tank to the center of area is half of that 6 feet or 3 feet. And since you have 3 feet of submergence, the depth of submergence to the center of area is the 3 feet plus the 3 feet or 6 feet. Once we know the depth of submergence to the center of area, we can calculate the pressure at the center of area. With the pressure at the center of area of the projection, we can get the force on this horizontal projection, and that's the horizontal force. Your question? Good. So, continuing. The horizontal force is going to be the pressure in the center of area of the projected surface into the vertical. That's the 6 foot by 1 foot rectangle. Times the area of that 6 foot by 1 foot rectangle. So it's the pressure times the area of the horizontal projection. So there's our curved surface, and as I drew on the last one, we're going to project it into a vertical plane, and it looks from the edge, before all we saw was a quadrant of a circle. When we project it, it just looks like a vertical line, but if we look at it from the side, we will see this rectangle that's 6 feet high by 1 foot wide. And what we're doing is calculating, again, knowing where the center of area is, we're calculating the horizontal force on that projection. So the pressure at the center of area is the depth of submergence of the center of area, which we identified in the last slide to be 6 feet, times the specific weight of water. So gamma H is the pressure at the center of area. And then we multiply it by the area, 6 feet high by 1 feet in depth. Again, it's a force per unit width, if you will. And that gives us 2,246 pounds. So again, there's the pressure at the center of area, the horizontal projection, and there's the area of the horizontal projection. Okay. So for the vertical component, again, fluid is below this. And so the pressure distribution, again, is everywhere normal to the surface, and therefore the resultant force is normal to the surface. And the vertical component, because all the pressure is pushing up on this, the vertical component is pushing up, it's representing the volume displaced by the surface. The volume displaced is that cross-hatched area. A1 is the area, it's a rectangle, and A2 is a little sliver. And when we multiply those by the 1 foot of width, we get a volume. That's the volume displaced. So again, the vertical force is the weight of the fluid above or displaced by the surface. The weight will then be the specific weight of the fluid, and this is that volume, in this case, displaced. And that volume displaced, as I indicated, is the total area, A1 plus A2, times the width into the board, 1 foot. And so we need to find that area. We know everything in that equation, the specific weight of water we know, and that 1 foot of depth we know. And so what we do is the total area A, we're going to break into the components A1 and A2. If you look at this, A1 is 3 feet by 6 feet. Right? And so A1 is 6 feet by 3 feet. That's the easy one. A2 is a little more complicated, and how we can calculate A2, and therefore volume 2, would be to take that square, 6 foot by 6 foot, and subtract out the quadrant of a circle, and that leaves A2. So in this case for A2, this is the square, and this is the quadrant of a circle. So the area of a circle is pi r squared, the quadrant of a circle will be 1/4 of that. And so now we have A1 and A2, and we can add those together to get the total area, which I had above. And with that, we can then calculate the vertical force. So our total area displaced is 25.73 feet. And when we multiply that by the 1 foot of width, the volume displaced would again be those two areas, A1 plus A2, times the width, 1 feet. Question?
Just a quick question. For A1, where did you get that 3 feet? Where's that measurement?
That's just given in the problem. So, for example, instead of 3 feet, I could have said you had a pressure here of 1.2 psi. So it could have been a closed tank. And for the closed tank, you wouldn't do the problem any differently. You would need to identify where a free surface is, so you could identify either the volume physically above the surface or the volume displaced. Okay, so in this problem, it's just given information. If you had that tanker truck, very often they're under atmospheric pressure, but you could certainly have a tanker truck that's put under pressure. For example, LNG, liquid natural gas, could be under pressure. And again, you wouldn't have a free surface of that liquid natural gas, you'd have it under pressure. So the same thing. That's just giving you information. You need to solve the problem to either get the pressure at the center of area for the horizontal projection or the volume displaced. Okay. The other way, instead of, that would be a manometer, right? That's all it is, a manometer. I said it could be a pressure gauge. It could be a barometer or a manometer, you know, one of those weird manometers. They're all different ways of giving you the same information. That's what you would expect to see on, say, the FE exam or in homework problems here. But when you leave here, they probably would have some kind of pressure gauge. That's the most logical thing. So, same problem. The vertical component, we've already solved the horizontal component. The vertical component is the specific weight of the fluid times that weird looking V with the line through it is the volume displaced. For volumes, I usually put a V with a line through it because we have a lot of V's in this course, for example, velocity, as you will say. So again, specific weight of water, 62.4 pound per cubic foot. And then the volume displaced is the 1 foot of width. And then the area, the total area displaced was 1 foot, A1 plus A2. And so that gives us a vertical force of 1,606 pounds. And remember, these are vectors, so when you write them, you should probably have the direction with them. The previous one was acting to the right, and this one is acting vertically upwards. So again, that line of action of FV is vertically upwards since it represents the fluid displaced by the surface. Again, think of the pressure distribution everywhere is pushing up on the surface. And the component of the vertical portion of that pressure distribution is upwards. So the magnitude of the resultant force, you now have the horizontal component and the vertical component. So this is your old friend, the Pythagorean theorem. The total force magnitude is the sum of the squares of the two components, square root. So when we multiply that out, the horizontal component, or I was calling that Fx before, sorry if I switched over, 2,246 pounds squared plus 1,606 pounds squared, square root, gives us a resultant force of 2,761 pounds. So remember, we have Fh, or Fx as I was calling it, 2246, and Mv of 1606 pound. And the resultant force is this 2761. Right? And this looks like a right triangle. And that means we can either calculate alpha or theta to identify the exact line of action and the exact point on the surface where this force acts. And again, typically we need to know the line of action and where a force acts when we're doing a moment equilibrium. Okay? And we had gone over that with forces on plane spin surfaces. So fundamentally, because everywhere the pressure distribution is normal to the surface, this resultant force is normal to the surface. So this is the exact force diagram I indicated before. And again, we have angles alpha and theta, and we can calculate exactly what those are. So sine of alpha would be 1606 over 2761. Sine of theta, or tangent of theta, or cosine of theta. We know all the sides. Question?
Yes, so someone wants you to clarify how you know the direction of FH and FB.
Excellent question. So the question was, in case you don't know, how do you know the directions of FH and FB? What I'm going to do is, oops. Yeah, let's start here. So this was our surface. And for the horizontal force, what we did was project into a vertical plane. And remember, the pressure distribution is everywhere normal to the surface. So we have this curved pressure distribution, and the resultant force, again, has to be normal to the surface. Since for the horizontal force, Fx or Fh as I called it later, you have a vertical surface. The horizontal component is the horizontal component to the resultant vector F. That resultant vector F that we just calculated is normal to the surface, pointing at the surface, because the pressure distribution points at the surface. Therefore, it must have horizontal and vertical components in these directions because of how the resultant force is pointed. Okay. And if there's more on that, just let me know.
Thank you.
Okay, that's where we were. So again, knowing all three sides of a right triangle, what we can do is, for example, for that horizontal, the angle of that resultant force off of the horizontal, tangent of alpha is the vertical force, the 1606 pounds divided by the horizontal force, or when we resolve this, alpha is arctan FB over FH, which gives us alpha is equal to 35.6 degrees. If you don't like doing it that way, we can solve for theta. So for example, the tangent of theta would be the horizontal over the vertical, the way we define theta. And you would find theta to be 54.4 degrees. And as you know, the sum of the angles in a triangle should sum to 180 degrees. Since it's a right triangle, one of those angles is 90 degrees, which means the sum of the other two should be 90 degrees. 35.6 and 54.4 is 90 degrees. Nice simple check. So again, we just solved theta and we just solved alpha. What we want to know is exactly where on this surface is this force acting. Again, if we have to do a moment equilibrium, we need to know not only the line of action, but maybe the distance to a point about which we are taking moments. So again, this is our triangle, and we have this resultant vector F, and it's got components in the horizontal direction. Again, I was calling it Fx originally, and I switched over to Fh and Fv. And we have similar triangles in that we have a hypotenuse of 6 feet. And what we're looking for is what's the distance on that same triangle. So again, you have a force triangle, and then you have a dimensional triangle, and they're the same triangle. So again, the force triangle is 1606, and this was, I'll just go back, get a break, 2246. And 2760. And those are all in pounds. And then what we're saying is, by analogy, we have this triangle 6 feet with angles alpha and theta, and we're trying to find this distance h by similar triangles. And if we know what h is, then we know what YCP, distance to the center of pressure from the free surface down to that same point. That's why we're going after h. We did not develop an equation for YCP for a curved surface. The only equations we have for YCP are for plane submerged surfaces. So one way around this is just to look at the forced triangle, and you can do this with any curved surface. Once you get the forced triangle, the horizontal, vertical, and resultant force, you can calculate distances from the analogous dimensional triangle. And when I say that, I'm talking about trying to find the exact location, horizontal and vertical. So we know that the sine of 35.6 degrees, and I'm just going to go back to the previous one. So the sine of this angle is going to be opposite h over the hypotenuse, 6 feet. Okay, so again, that's what we have here. And what we want to do is solve that for h. So h is 6 foot sine 35.6 degrees, that's 3.49 feet. So we know the line of action of that vector. It is perpendicular to this curved surface. The curved surface is a quadrant of a circle. If the line of action is perpendicular to the curved surface, it goes through the center of the center of curvature, the center of the circle. So on all of these previous figures, again, that force goes through the center of the circle. It has to, because it's normal to the surface, because this is a quadrant of a circle. If it's an ellipse, of course, this is not true. And then if you wanted the depth to the center of pressure, we know that the total depth from the free surface to the very bottom of the system is 3 feet plus 6 feet. That's 9 feet. H is the dimension from the bottom all the way up to the center of pressure. So if we just subtract the 9 feet of total submergence from the, and subtract off what we just calculated to the vertical distance to where this force acts, we can get YCP equal to 5.51 feet. So again, if our tank looks like this, this distance is 9 feet. We just calculated h, and that was 3.49 feet. And so what we're calculating is YCP. the vertical distance down. And so you can figure out exactly where this is. And if you have to do a moment equilibrium, now you can figure out distance to whatever point about which you want to take moments. So if we compared this to a plane surface, so you say, screw this, I don't want to deal with a semicircle, I'm just going to look at this as the flat end of a tank. And I don't want to run through all these numbers, I post these, as you know, you could look through this. But basically what would happen is you would get a smaller force. And the reason for that is when you go with the plane surface, you're neglecting all of that volume displaced. And so you're coming up with a much different vertical component. The horizontal component would be the same. So again, it's dangerous to just make simplifications like this. It's not too challenging to calculate the vertical and horizontal components on the regular geometric objects. When it gets complex, again, I don't know why you'd be doing something complex, but if it did, just break it into composites like we talked about before. Last week we talked about, for example, a figure that looked like this. And what we did was break it into two pieces. You can do the same thing with any curved submerged surface. Break it into pieces that are manageable. Okay, so in the last 10 minutes, I want to introduce buoyancy in flotation. So what we've been covering is forces on planes submerged objects, two-dimensional objects. Now we're talking about three-dimensional objects. And when we talk about three-dimensional objects, there are forces associated with them, but now we have to consider that third dimension. So for conceptually understanding this, I'm going to take a floatable brick. And this floatable brick is lighter than water, so here's a little brick. And that little brick is lighter than water, and so what you see is it's floating. And it's only submerged some distance, which I'm calling h. Sometimes that's also called the draft. Okay. So this brick happens to be having dimensions dx by dy by dc. So it's easy to calculate the volume. What we know is, since it's a nice simple shape, and it's a nice simple brick, and it's of uniform material, it's going to be floating horizontally. If it wasn't uniform material, it could certainly not be horizontal. But just to develop this, we're going to say the bottom's horizontal, which means that you know the pressure at the bottom. If you have a depth of submergence from the free surface of h, then the pressure at the bottom should be just the specific weight of the fluid times h. And it's constant all over the bottom. So we have this differential sized brick, dx by dy by dc. It's under a submergence h, and the pressure at the bottom is gamma h. From that, we can calculate the force at the bottom. Now, force is equal to the pressure at the center of area times area, right? But the pressure all over the bottom is the same. It's not only at the pressure at the center of area, the pressure at the bottom everywhere over the bottom is the same. So we're not violating what we developed before. This is just a very unique situation where all of the pressure distribution happens to be the same. So the pressure at the bottom times the area of the bottom would be a force. And that force is pushing upwards because the pressure distribution everywhere is normal to the surface, pointed upwards. And since we know that that force at the bottom is the pressure at the bottom of the area, and we can substitute gamma h for the pressure, then the force on the bottom is gamma ha, the specific weight of the fluid, whatever it is, times the depth of submergence, times the area of the bottom of this, which would be dy by dx. If you look at those second two terms, H times the area is this volume. When we were just talking about curved surfaces, we called that the volume displaced by the surface, right? And this is no different. This is the volume displaced. Instead of a surface, it's a volume. But it's the fluid volume displaced, or the displaced fluid volume. And so that force, FB, is equal to the specific weight of the fluid times the volume of fluid displaced by this object. FB is known as the buoyant force, and it acts on any partially or completely submerged object. So, what's the pressure? Now let's have a quiz between chat and in class. What's the pressure distribution on the top? And not a lot of hands here. Atmospheric, right? So there's just air above it. Could it be another fluid? Absolutely. And if it is another fluid, that's another thing we'll get to. But right now, for a floating object, it's just air. So if you're operating in the gauge pressure datum, which we almost 99% of the time do, you don't have to include atmospheric pressure. If you are working in absolute pressures, then you have absolute pressure on the top and the bottom. It's going to cancel out. Okay, so in the vertical direction, the floating object is in equilibrium. It's just sitting there minding its own business. And what that means is, if we performed a free body diagram and we looked at a force equilibrium in any direction, the sum of the forces are zero. But in this case, we're specifically going to be looking at the vertical direction, and typically upwards is our positive z direction. So some of the forces in the vertical must be zero for this floating object. And again, the upwards force is due to the pressure distribution at the bottom, and we call that the buoyant force. And in this case, if we look at a free body diagram, here is our brick. It's got a weight, and it's got the buoyant force operating on it. Those are the only two forces in the vertical direction, because this is sitting there, it's not moving. And so in this case, again, if z is positive upwards, this would equal to the buoyant force minus the weight, or the weight is equal to the buoyant force. An object displaces an amount of fluid equal to its own weight, Archimedes' principle. So we can calculate the buoyant force, and the weight we can always calculate. The weight we can calculate, it's either given to you in problems, or if you know the volume and you know the specific weight of the material, wood, concrete, steel, the weight is going to be the specific weight of the material times the volume of the object. And we've calculated that before here. So again, the buoyant force acts on any submerged or partially submerged object. And we'll talk about both. The buoyant force is basically representing the difference in the pressure distribution from the top of the object to the bottom, whether it's submerged or unsubmerged. So again, if you have a submerged object, there's our free surface. We've got a pressure distribution on the top, and we've got a pressure distribution on the bottom. And because pressure increases with depth, the pressure on the bottom is always going to be at least equal, but usually greater than the pressure at the top. When the two are almost the same is when the object height becomes smaller and smaller and smaller, infinitesimally small. But in general, when we have height to a physical object, you're going to have a greater pressure on the bottom than the top. And the buoyant force is basically that difference in pressure distribution integrated over the entire surface of the object. All right, second quiz for on class versus chat. If I wanted to calculate the horizontal force on this side, I could shine a light and project it onto the wall and calculate the horizontal force just as we did before on curved surfaces. If I then wanted to calculate the horizontal force on this side, I could shine a light onto a vertical plane and calculate the horizontal force on that one. What do you think the difference in the shadow will be going from the left or to the right? Is there a difference in the shadow? No, it's going to be exactly the same. So the horizontal forces are all the same. So when you pour your bathtub and put the little rubber ducky in there, if everything's quiet, that object should sit there. If it's moving, it's around, it's because there are probably some remaining currents in the water. But if it was perfectly still, it would just sit there. So we don't typically worry about the horizontal forces in these situations because no matter how you look at it horizontally, it should all cancel out because the shadow is the same in either direction. Okay. When the object is completely submerged, the displaced volume is equal to the volume of the object. That's kind of self-evident. So if this were floating, I would need to know how much the object is below the floater. But if this is completely submerged, then the buoyant force is related to the total volume of the object. So heavier objects are lighter in water. Question.
Would you mind just taking like the last like 2 or 3 minutes of class, just give like quick bullet points about exam, just so we can kind of like hone in our study these last couple of days?
That's a
before?
good point. So you don't like lecture anymore, so you want bullets on the exam. The exam is going to be incredibly similar to homework problems. So it's not going to be any derivation. Typically what I've done in this course is go over theory, break it down to practical application, and then you see these different types of problems that typically ask for one of the components of an equation we developed. Your most challenging issue is to be able to distinguish between the different facets of the course we've talked about. For example, we talked about fluid properties. For example, compressibility versus forces on submerged objects. So if you see something asking for a force, it could be a fluid property problem. For example, when we talked about shear or compressibility, you could do a force there versus forces on plane submerged objects. So the first thing you want to do is distinguish. Is this a fluid properties problem? Is it a fluid statics problem? So for example, if you see a manometer, you should know that's a fluid statics problem. You should recognize it. So you shouldn't go and try to figure out what's the specific volume of the fluid just because I gave you the density. That's not going to help you at all, although it's a calculation. So that's the next thing. If you have performed all of the homeworks, which we grade, of course you've done that, but also the ones in the book, you'll be fairly well prepared if you can do them by yourself. The one thing this COVID thing has done is probably made you study more on your own than in groups like in the past. And I think this material, the only way to really learn it is to do it repetitively. And that's what the homeworks are trying to do for you, build that. I would say, look at the economics of an exam. This is probably the most important, valuable information I can give you. Look at a problem. If you know how to do it, do it. If there's any question in your mind, skip it and go to the next one. We give partial credit. Sometimes the TAs give more partial credit than I care for, but I don't look over their shoulders when they're grading. At the end of the exam, then you go back to the problems you skipped and then try to attack them. Leaving a blank problem is easy for us to grade, but gets you no partial credit. So if you think it's a force on submerged problem, start setting up the equations. Draw a diagram, do a free body diagram. And even if you don't calculate things, you know, most of engineering is being able to set it up right, setting up a problem correctly. Anybody can do the calculations afterwards, and that's where they can check and see if you miscalculated. But if it's set up wrong, fundamentally everything's wrong. So set up the problems would be the next one for any ones you couldn't attack. And then don't spend any more than 15 minutes on a problem. There will be anywhere from 5 to 10 problems on this exam, it's somewhere in there. They're very similar to the homework problems. So if you have 2 hours to do this, let's say there's 10 problems, then you have 12 minutes per problem. If you spend 15 minutes on a problem, what you're doing is penalizing yourself. Yes.
I have a couple of questions about the exam. The first one is some of the students ask about the office hour till Friday.
I'm generally around. I'm being tugged in a lot of directions now, but if students want to email, call, or set up a Zoom, I can do that. I realize I couldn't do the second review session as I promised, but I'm generally available most hours of the day.
The second one is there any class on Friday?
There is class on Friday, but that material is not covered on the exam. So we lost a week. I need to keep that up. So,
The next one is some of the students ask for the homework's answers.
they want the
beside
solution.
there.
So
Yeah.
that's a common request. And I know some of your other professors post the solutions. This is my sentiment on posting solutions. When I post solutions, not all of you, but some students use that as a crutch. And what they'll do is look at it and say, I see that. And that's not building your own capabilities. So in the grading of the homework that we grade, you are given enough information to understand where you went wrong and calculate the right answer. On the homework problems I don't collect, again, the answer is in the back of the book, but those are the ones if you want to ask me, again, telephone, email, Zoom, we can certainly go over how to set them up. And that's how I did the first review session. Only 2 people attended that review session, but when people say, can you do problem 321, all I do is set it up. I don't work through and calculate it. Because again, setting it up is 80% of the grade. If you can set up all the problems on the exam, you're starting at a B, setting them up correctly.
The next one is you said the exam will be like the homeworks. So the homeworks they posted from 1 to 9 or all the homeworks inside the book?
All the homeworks that we have graded today, 1 to 9, and all the relevant homeworks that line up on the syllabus with all the material up through and including forces on plane submerged surfaces.
And the next question is there any short answer question inside the exam or just calculation?
I mean, that's, the question was, are there any short answers? And my answer to that is, short is in the eyes of the beholder. So to me, yes. To you, to me, if it takes 10 seconds to set up and solve, but again, I've been doing this for a few decades. For you, if it takes more than 2 minutes, that's a long, and less than 2 minutes, that's a short. So yes.
And the last question, will there be any logarithmic graphing?
This exam, you should be able to do with a pencil, paper, and a calculator. So you shouldn't have to be plotting up something. So I'm not going to ask you to do a regression and give me the coefficients A and N to a power function. I think the idea of the labs is to get you to do that there and not beat that into your head. Lab 1 was specifically on the log plotting, so I think you know how to do that now. There must be more. I think I set these Zooms to end at like 12:10, so I've got a few more minutes.
Someone's asking if there will be any multiple choice questions.
No multiple choice.
And people were asking about a review session this week. I assume there's not one, but I just want to double check.
There will not be a review session just because I haven't had the time to set it up. If I can set one up, it would be tomorrow night, but it will be challenging for me to do that. And if I do set it up, it will be a Zoom, and it will probably be, say, late afternoon to evening. Have we exhausted questions? All right, you know how to find me. Good luck.
meeting Friday.